Hello friends. So today I'm going to discuss about the different factors that affect the enzyme action. Eventually, those factors affect the rate of the enzyme catalyzed reaction. So various factors which I'm going to discuss. So these are pH, temperature, concentration of enzyme, concentration of substrate, oxidation state of enzyme, presence of cofactors or coenzymes, and lastly the presence of inhibitors. So first factor that I'm going to discuss is the pH. So every enzyme, they work in a particular pH, and they have, in that particular pH, they have got the optimal activity or maximum activity. Say for example, most of the enzymes present in the mammalian body, so their optimal pH is 7. This means that they have the optimal activity when pH is 7. So for example, let us take a small example here. Say at pH 7, this is an enzyme, and this part of the enzyme is an active site, and this is the substrate. So as per the induced fit model, so the active site of an enzyme is almost complementary to the structure of the substrate. So now at pH 7, this enzyme can bind the substrate. When we raise the pH, let's say we raise the pH to 9. So in this case, what happens? There is a change in the structure of the active site of an enzyme. As a result, when there is a change in the structure of the active site of an enzyme, so the active site is no longer complementary to the structure of the substrate. So the substrate cannot bind. So that means same thing happens if we decrease the pH below. Let's say we decrease the pH to below 5. So in that case also, the active site structure will be altered, and also in that case also same thing, the enzyme will not be able to bind its substrate. So now this enzyme will be able to bind the substrate only in this particular structure. This particular structure is maintained at pH 7. So pH 9 and pH 5, the structures are altered, and as a result they cannot bind. Hence we call this as the optimal pH. Now the next comes is the temperature. So just like pH, every enzyme, they have got an optimal temperature. For example, most of the mammalian enzyme, their optimal temperature is 37 degrees Celsius. So at this temperature, so they have a structure which can bind the substrate. If we increase the temperature, let's say to 50 degrees, so in this case, what happens when you increase the temperature to 50 degrees? So there is a alteration in the structure of the active site, just like pH. So in that case, since the structure of the active site is altered, so it can no longer bind the substrate, and that will lead to decrease in the rate of the enzyme catalyzed reaction. So that means at 37 degrees Celsius, enzyme maintains its structure that can actually bind the substrate. Now let's move on to the next factor. The next factor is the concentration of an enzyme. So high concentration of enzyme will have the higher rate of enzyme catalyzed reaction. Now let us take an example. Supposing that we have, so here the S stands for substrate and E stands for enzyme. So we have 100 numbers of substrate molecules, but we have only 20 numbers of enzyme molecules. Now in this case, what will happen? At a time, only 20 numbers of substrate will bind the enzyme molecule, and rest 80 numbers of substrate will not bind the enzyme. So hence there is the rate of reaction is somewhat less. Now if we increase the number of enzyme molecules, say we have increased the number of molecules from 20 to, let us say we have made it 40. So once we have increased the enzyme molecules, now more number of substrate molecules will be able to bind the enzyme. So as a result, that will increase the rate of enzyme catalyzed reaction. Then similarly, if we just go on increasing, and let us say that we have 100 molecules of enzyme. We have increased the concentration of enzyme to 100 molecules. So in that case, every substrate molecule will be able to bind the enzyme. So hence the rate of reaction will further increase. That means when you increase the amount of enzyme, okay, in relation to substrate, so what will happen? More number of enzymes will be available to bind the substrate, and that will further increase the rate of reaction. But if the enzymes are less, the concentration is less, so that means less number of enzymes will be binding the substrate, or less amount of enzymes will be available to bind the substrate, and that will eventually decrease the rate of reaction. So we just increase the amount of enzyme molecules, so the rate of enzyme catalyzed reaction will go on increasing. Then next is the substrate. So in this case, we assume that the concentration of enzyme is constant. So in the constant concentration of enzyme, so in that case, what happens when you increase the substrate concentration, the rate of enzyme catalyzed reaction increases. Now let us say we have 50. This is the analogy you're taking. Say we have 50 number of kids, and then we have only 10 numbers of chocolates. So now we have 10 numbers of chocolates only. So what will happen once we approach these 50 kids and we say that we have 10 number of chocolates, just give them the chocolates. So what happens? Out of these 50, all of the kids, 50 kids, will fight among themselves. Then only 10 kids will be able to take the chocolate and they will eat the chocolate. Let us assume that for eating one chocolate it takes only 1 minute, but the kids have taken 10 minutes. How is it possible? It is because the 50 kids, out of 50 kids, only 10 kids were able to eat the chocolates. So how they ate the chocolate? Because those 50 kids, they will fight among themselves. So they have taken about 9 minutes in fighting among themselves, and out of these 50, 10 kids were the winners who got the chocolate. Now to fight for the chocolate, they wasted about 9 minutes. On the other hand, if we have the 50 kids and if we give them 50 number of chocolates, so in that case what will happen? Every kid will get one chocolate. So in that case there won't be any fighting and they will finish the chocolate within 1 minute. That means in earlier case what happened? The number of chocolates were less, so there was a competition among the kids, and that competition led to increase in the time to eat the chocolates. Now similar kind of thing, this analogy, now it works in this particular example. Let me erase all these things. Yeah, so okay, now let us assume that we have 10 numbers of substrate molecules and we have 100 numbers of enzyme molecule. Now in this case, just like we had 50 kids and 10 chocolates, same thing is here. Now we have 10 numbers of substrate molecules and 100 molecules of the enzyme. So these 10 molecules, when they are added to the enzyme, what will happen? These 100 enzyme molecules, they will compete among themselves to bind to the substrate. So as a result, what will happen? The rate of reaction will be less, because the rate of reaction is less because of the competition that is occurring between the 100 enzymes. Now you just increase the number of substrate molecules from 10 to 20. If we increase the concentration of substrate from 10 to 20, now what will happen? We are giving more number of substrate. So now still there will be competition, but the competition will be less as compared to that when it was 10 substrate. Now just go on increasing the amount of substrate from 20 to, say, you have made 50 substrate molecules. same enzyme. So now 100 enzyme molecules we have, so 50 substrate, so 50 enzyme molecule will bind this substrate, rest 50 will not. So now when you are increasing the amount of substrate, so there is a decrease in the competition between the enzyme molecules, and then what will happen, the enzyme catalyzed reaction, the rate of reaction will go on increasing because competition will decrease and the rate of reaction will go on increasing, and the rate of enzyme catalyzed reaction will reach maximum when the amount of substrate and the amount of enzyme is equal. That means every enzyme gets equal number of substrates. So that means no enzyme is free now. Every enzyme gets, so in this case the competition will be zero competition, because just like earlier case, 50 kids, 50 chocolates, no competition, so they will finish the chocolates very early. Similarly here, when you have the 100 numbers of chocolates, 100 numbers of substrate and 100 numbers of enzyme, so there is no competition. So now the rate of enzyme catalyzed reaction will be maximum. Now if you go on increasing the substrate, say you made it 150, so now still the enzyme catalyzed reaction rate will be same, because enzyme concentration is constant here. So out of 150, 100 will bind the enzyme, rest 50 substrate will not bind. So your rate of enzyme catalyzed reaction has reached the maximum velocity because all enzyme molecules are saturated. Now the next is the oxidation state of the enzyme. So what is the oxidation state of the enzyme? So oxidation state of the enzyme, every enzyme molecules or every biomolecule, they are subjected to a reaction called oxidation. So oxidation is done by the oxidizing chemicals, or the most important oxidizing compound is the molecular oxygen. So now every enzyme, they have got an amino acid called cysteine amino acid. Most of the enzymes, they have got cysteine amino acids in their active site. So these cysteine amino acids, as you know, that they have the sulfur hydryl group, SH group, in their side chain that many times interacts with the substrate. That means the SH group present in the cysteine amino acid, they interact with the substrate. Now when they are oxidized, that means oxidized means removal of the hydrogen. So when from SH group the hydrogen is removed, so this removal of the hydrogen from SH group leads to formation of a disulfide bond with other cysteine amino acid, and this disulfide bond is formed when the hydrogen is removed, and as a result this leads to alteration of the active site. So you can understand that like this. Say this is the cysteine amino acid and this is the terminal SH group present in its side chain. Now when it reacts with the molecular oxygen, so what happens? This molecular oxygen, it oxidizes the SH group of the cysteine, and then we have cysteine S, bond is free, plus H2O. So here the reaction is not balanced. I've not balanced the equation. So now what you have a cysteine amino acid where the hydrogen is removed. So now the sulfur, the bond is free. Now in this case, what happens? When you have the cysteine amino acid where the sulfur bond is free, similarly you have another cysteine amino acid in the same protein. The same protein, you have another cysteine amino acid from where the hydrogen is removed, like this. Now what happens? These two bonds are free. As a result, they form the disulfide bond. Sorry, that I'll have to erase this. So now this one cysteine, this sulfur. Now this forms the bond with the sulfur of the next cysteine amino acid. So now there is a formation of the disulfide bond. And how this affects this formation of disulfide bond between two cysteine amino acid, how it alters the structure of the enzyme. So let me erase this, then it will be clear. Okay, now what happens? Say this is the enzyme molecule and this is the active site. So at this part it has got a cysteine amino acid, and at this part it has got another cysteine amino acid. Now this enzyme is in contact with the oxygen. Now we have seen that the oxygen removes the hydrogen atom. So as a result, what will happen? Once the hydrogen atom gets removed, say from this, the hydrogen gets removed upon exposure to oxygen. So now you have two sulfur without hydrogen. So what will happen? These two sulfur of cysteine, they will form the disulfide bond. So as a result, you will be having an enzyme like this. This is the active site, and you have, this is the sulfur, this is the sulfur of this cysteine amino acid, and they form the bond. Now when you have this kind of structure where the two cysteine amino acid was originally present far away from each other, now they have formed the bond. Now the substrate cannot enter this kind of active site because the structure is altered. So that is why the enzymes are always kept away from the oxidizing agents. So this is the one of the harmful effect of the excess oxygen circulating in the body. Well, now the next factor is the presence of the cofactors or coenzymes. So many enzymes, they need cofactors or coenzyme for their activity. So these enzymes will not work if in absence of the cofactors. For example, the Taq polymerase enzyme, which is required in the PCR, it requires the magnesium as a cofactor. If magnesium is absent, Taq polymerase will not work. Similarly, another enzyme of the TCA cycle, that is called succinate dehydrogenase, requires FAD as a coenzyme. If FAD is removed, then the enzyme will not work. So how these cofactors or coenzymes work? So let us say this is the enzyme, and this particular site is the cofactor binding site. So when the cofactor binding site is empty, so active site, its structure is not complementary to the structure of the substrate, so substrate cannot enter. Now when this cofactor, it goes and it enters the cofactor binding site, then what happens? This enzyme active site, this gets opened. So when the cofactor binds, the enzyme active site gets opened, or its structure becomes complementary to the structure of the substrate. That means when the cofactor is not bound to the enzyme, the active site structure is not complementary to the substrate. As a result, the enzyme cannot carry out the reaction. So let me show this diagrammatically once again. So I'll just erase everything, then I'll show this in the diagrammatic way. Say for example, this is the enzyme and this is the cofactor binding site, and this is the substrate. Substrate cannot bind because enzyme active site is not complementary to the substrate. Now this is the cofactor. Now when the cofactor, it goes and bind the cofactor binding site in an enzyme, so this leads to alteration in the structure of the enzyme active site. So now the enzyme active site structure gets altered. So now it assumes a new structure. So this new structure is complementary to the substrate. And now substrate can go and bind. So this for the substrate, substrate can go and bind. So same thing is a coenzyme. If the coenzyme is absent, the enzyme cannot work. The next factor is the presence of inhibitors. So the inhibitors are the small molecules which slow down the reaction of the enzyme catalyzed reaction. So for example, so we have different types of inhibitors like competitive inhibitors, non-competitive inhibitors, uncompetitive inhibitors, irreversible inhibitors. So this is the topic of discussion in the next video. So basically the inhibitors, they bind the enzyme and then they alter the structure, and as a result they cannot carry out their reaction. So example is the enzyme enolase. Enzyme enolase of glycolysis is inhibited by the sodium fluoride. That means whenever we take out the blood to estimate the blood glucose, so in that case the anticoagulant that is used is the sodium fluoride. So sodium fluoride, what it does, this stops the glycolysis, because this sodium fluoride, it inhibits the enzyme enolase of glycolysis, and eventually this inhibits or it stops the pathway of glycolysis. So glycolysis is a process that utilizes glucose. So in the RBCs, the glycolysis continues. As a result, it will decrease the blood glucose which is obtained in the tube for analysis. So now to maintain the amount of blood glucose as it was in vivo, so the glycolysis of the RBCs is inhibited by using the anticoagulant that is called sodium fluoride. So I hope you like this video. If you like this video, please click on subscription, and if you want to get the information about new videos, please click on the bell icon. Thank you very much for your support and for your patience for listening to this video. Thank you very much.